So this video is a conceptual introduction to an idea or a way to keep track of an object or a system. This idea is called the center of mass, and the center of mass is often abbreviated COM or even CM. Yeah, but you probably know from context. But yeah, so it's a conceptual introduction. There is a way to calculate it. It's definitely a quantitative physical quantity. Yeah, and so later videos I'll show you how to calculate it and also what you can do with it, especially with respect to momentum and momentum conservation. So first of all, it's an idea for objects themselves, like for example, the Earth, or a person, or anything, a hammer. So the center of mass can be applied to an Earth, or person, or a hammer, but also it's an idea for systems of objects. And yeah, so I'm going to show you some examples of seeing the center of mass, or seeing something interesting about the motion of the center of mass. So I'll say the motion of the center of mass can be an interesting way to view a system or an object, and how that system or object is moving through space under the influence of force. So yeah, the motion of the center of mass. So here's an example. So an example is projectile motion. So let's say that somebody throws a rock, and you know this little rock is an object, and I'm telling you that objects have what's called a center of mass. So the center of mass of a nice spherical little rock is right in the middle of it. The center of mass is a position or a place. So center of mass is a location. And this location, we can think about the motion of that location. So in the particular case of projectile motion, the motion of that dot, here it is at different places. This is the trajectory of the center of mass of the little rock. But honestly, this is boring. It gets more interesting, right? Yeah, more interesting if the object itself isn't so boring in shape. So let's throw a hammer. So a hammer, you know, is this little sort of wooden handle with a little metallic head on it. And if you've ever held a hammer, it's really heavy on the metal end and really light on the wooden end. So when you throw this hammer, what's interesting is it's going to rotate. You know, if you throw it sort of willy-nilly, it'll rotate. You can cause it to rotate this way, or you can cause it to rotate this way. And the truth is it doesn't even need to rotate. It could just go like this, or like this, So, but if you do put it into rotation, what's interesting is it turns out that the center of mass is located closer to the heavy end of objects. So the center of mass of a hammer is up here. So I'll put the COM is right up there. And what's going to happen is when you throw this hammer, so let me pretend that we've thrown the hammer, and here is the trajectory of a hammer as a projectile. What you'll notice when you do this, when you throw a hammer, so let's throw a hammer, the hammer will do something like this. If it's got some rotation, maybe early in its motion, the center of mass is here. A little bit later in time, the center of mass is advanced along the trajectory, and the hammer is rotated about the center of mass. A little bit later in time, the hammer seems to be upside down. So the center of mass is this little dot. It's a place on the hammer system, right? And if you just follow the trajectory around, at some point, I guess it may look like this instead. And we're imagining this hammer, it's just rotating about the center of mass. So there is a rotation about center of mass, but what's more is the center of mass of hammer follows the projectile motion trajectory. So this is one useful or one way to view the utility of the center of mass. If you throw an object with an interesting mass distribution, right? So the hammer has an interesting mass distribution. It's massive on one end and quite light on the other. The center of mass is up towards the massive position, and the utility of the center of mass is, although the head of the hammer might have a really complicated motion, you can see that the head of the hammer is kind of swirling around the trajectory. The center of mass is actually quite boring in a sense. The motion of the center of mass is kind of easy. Okay, so let me go on and describe another example of thinking with the center of mass. This one's cool. This one is orbital motion. And there is a special word, and you can go look it up. I challenge you to check Wikipedia for this word, Barycenter. I don't know what the origin of this word is, but the Barycenter is a way that maybe astronomers talk about the center of mass, and it's the center of mass of systems of planets, stars, and moons. So so the center of mass idea can go all the way up and help people understand orbital motion. So here's an example. Here is the system of Earth and Moon together. And you'll see that the Earth and the Moon, in a sense, behave very similarly to a hammer, where the Earth is more like the hammerhead and the Moon is like the wooden handle. So check this out. The Earth is this spherically symmetric kind of massive object, a lot like this really boring rock. So it was boring because the center of mass just marked the center of the object. And the center of mass of the Earth is right dead center of the Earth, basically. And the Moon, you know, the Moon is really, really small. But its center of mass is at its center, essentially. But the center of mass of the Earth and Moon system is not at the center of the Earth and not at the center of the Moon. The Earth is like the hammerhead and the Moon is like the hammer's handle. The center of mass of the Earth-Moon system is right, I think it's here. If you go and you look on Wikipedia and you look for the center of mass, like you can just Google center of mass of Earth-Moon, it'll put it actually inside the interior of the Earth. So the center of mass is not out in the middle of space, and it's not close to the Moon, right? The Moon is too light compared to the Earth. The center of mass is somewhere just on the inside of the volume of the Earth. So the center of mass of Earth and Moon together, that's called the Barycenter. This is the Barycenter of the Earth-Moon. And this little Barycenter is what orbits the Sun in an ellipse. So here is the Sun, and here is the Earth and the Moon. But the Barycenter is the thing that marks out the trajectory or the ellipse. Let's go elliptical orbit. So the COM of Earth and Moon system travels the ellipse. The Earth, in a sense, spirals the ellipse. So the Earth path is interesting. It goes like this because, right, this little thing is itself, right, the Moon goes around the Barycenter of the Earth-Moon system. So weirdly, the Earth is kind of like going something like this. The Earth motion is complicated, but the center of mass of the Earth-Moon system is not complicated. It's the elliptical orbit.